Welcome to all of you. In this session, we are going to discuss about mm, the paper 6, paper 7, that the chemistry in the branch of inorganic chemistry. We are going to focus on that chemistry of newer materials. In that we have so many metals, conductors, superconductors, fullerenes, and nanomaterials, like that. Now in this session we are going to discuss about the nanomaterials. It's in this chapter, in this session we are going to discuss the what are nanomaterials, what is the applications, how we are going to prepare the nanomaterials, what are the methods available for the preparation of the nanomaterials. You know that nowadays we are very much interested about the nanomaterials. Everywhere you go for, actually we are going to apply for nano. In the food industry you go for nano, in pharmaceutical you go for nano, as well as wherever you go for, we are going to apply for the nanotechnology. What is that nano? Yeah, look at now the nanomaterials. In that particular this one session, I'm going to mainly focus on that, the introduction, definition and structure, different methods of production, and how we are going to prepare using that one. We have totally 5 methods for the preparation of nanomaterials as per your syllabus. Here we are going to make it for the 2 methods I'm going to concentrate in this session. Remaining we can look after for the next session. Here the first method is sol gel synthesis and another one is inert gas condensation. Now we go for the what is nanomaterials. What is nanomaterials means, you know that any substance, any things we are going to use for the our routine or everywhere we are going to use for. Materials means things or substance. Then what about nano? We are already using so many materials, but we are going to apply for here now the nanomaterials. What is that nanomaterials? Nanomaterials are the materials which having a single unit. And the nanomaterials is nothing but it's having a single unit. You can take any dimension, any size. It's a single unit sized in one dimension. And then you can take one material, it's having a only single unit. We can consider as a single unit. It's having a between the size 1 to 1000 nanometers. That means, yeah, that's the nano means, you know that if you go for measure the meters, millimeters, micrometers as well as nanometers. Meter we are going to take it as such, we have to convert the millimeter 10 to the power of minus 3. We have to convert the micrometer 10 to the power of minus 6. Here we are go for further 10 to the power of minus 9. It's that we can call it as a nanometer. Nano means 10 to the power of minus 9. Then further we can go for 10 to the power of minus 12. It's a picometer. But it's usually what I given, actually it's a single size dimension between 1 and 1000 nanometers. But actually the substance what we are going to use, actually it's around 1 to 100 nanometer. That's all. The useful definition of the nanoscale, that's what we are going to use for the nanoscale. That's what we are going to get actually. And the materials what we are going to get now, yeah, the nanoparticles are a great interest. You know that nowadays you are going to see everywhere it's the nanomaterials. It's a very interesting because of the size we are going to reduce the size of the particles, size of the material, or everywhere you go for, you are going to apply for the same thing. You are going to apply for the nanomaterials in pharma industry, in drug industry, or in what is that materials, whatever you are going to take it, actually because of that size we are going to reduce the size 10 to the power of minus 9. It's indicating the quantity, as they are effectively a bridge between bulk materials and as well as the It's a what is that? What is they are going to do now? Yeah, they are going to make it a bridge between the bulk materials and atomic or molecular structures. The nanoparticles are their effective bridge between the bulk materials, atomic or molecular structure. That's why we are going to make it for the nanomaterials having so much interest on that. What we are going to get actually. Now, structure of nanomaterials. Here in that nanomaterials we have two kinds of structure, 2D structure as well as the 3D structure. You know that nowadays when you're going to saw the movies, we can see the 2D dimension as well as 3D. That's what we are going to get actually. HD. That's all what we are going to get actually. Now here we are going to study the nanomaterials in two dimensions. Here two dimension as well as the 3 dimension. Let us see what is the 2 dimension and what is 3 dimension. Here 2D stands for 2 dimension. The materials are crystalline materials. That is, if you go for 2 dimensional material, they are having a consisting of the crystal in nature and as well as a 2 dimension single layer atoms. 2 dimension having a single layer atoms. The most important representative graphene. Here the most important material for the 2D material is graphene, is discovered in 2004. Other 2D materials based on the other elements have since been reported. Afterwards other materials are become in forward the after 2004. Now this is what we are going to get actually. Another one is 3D elements. In that 3D we are going to get actually BSG. Short form we can call it as a BSG. That is a BSG full form, box shaped graphene. Here that what we did in 2D, it's a 2-dimensional sheet, single unit structure. But in 3D shape we are going to make it for the box shaped structure. That's the for nanomaterial. In that case we are the mechanical cleavage of pyrolytic graphite. That's what we are going to get actually, the what we are going to use for the graphite. In that this surface whatever we are going to get actually 2D as well as 3D, that's having the surface having a quadrangular cross section. That's the main advantage here. Now that's what we are going to take it for 2D and 3D structure of the nanomaterials. They having a quadrangular cross section. The thickness of the wall, that's what you are going to get. The main concept of that nanomaterial is actually its a thickness of the wall is approximately equal to the 1 nanometer. Look at now here, the 1 nanometer is nothing but it's very less, like our the one single air. That's what we are going to get actually. That size, that's what we are going to get actually. The typical width is about the 25 nanometer. See, look at now here, the thickness of the nanometer is having a 1 nanometer, and as well as the width of the channel, that's what you are going to take box, it's having a 25 nanometer, not for the meter. Here now you look at here now the listen, that's what you are going to get actually, it's a 25 nanometer. Now in this particular case here, these nanostructures are equal to the, now that is the basic definition of the nanomaterials as well as the structure of the nanomaterials, how we are going to make it for. Then continuation of that, we have different methods for production of the nanomaterials. In that I already told actually, we have mainly five methods available for the production of the nanomaterials. And in this session we are going to consider that main 5 sessions are sol gel synthesis, inert gas condensation, mechanical alloying, plasma synthesis, and electro deposition. You know all the terms here now. The sol gel synthesis, inert gas condensation, here are all the methods. We can go for one by one, but in this session I am going to concentrate only 2 methods. One is the sol gel synthesis and as well as inert gas condensation. Let us see what is sol gel synthesis. Yeah, now the short form of sol means it's a solution and gel means gelatin. Let's make it, we have a short form in that sol gel synthesis. You know that as a chemistry student, how we are going to make the synthesis of the particles. Yes, sol gel is a chemical solution process used to make the sheet like thin films like ceramic and as well as glass materials, fibers, films and as well as powders. I already told actually sol stands for solution and gel stands for gelatin. Here a solution is called or sol is called colloidal or molecular suspension of the solid particles of ion. Here the solution, whatever the solutions we are going to get actually are, it's a colloidal or molecular suspension. That is, you know that the colloidal particles, colloids, the molecular suspension of solid particles of ions in a solvent. They undergo for the hydrolysis and polycondensation reactions to form the colloid. That whatever the materials are there, they will undergo for the hydrolysis and as well as polycondensation. You know that hydrolysis is nothing but addition of water molecules or addition of water molecules, and condensation, polycondensation. Here condensation means you are going to combine two or more atoms, you are going to eliminate the smaller atoms. Like that polycondensation and more than one step what you are going to get actually. That system composed to nanoparticles dispersed in a solvent. You can have what is the, when it is undergo for hydrolysis as well as the polycondensation in the system, the composed of nanoparticles dispersed in a solvent. Solvents we are going to get for the nanoparticles. The solvent evolves then towards the formation of inorganic continuous network. Yeah, the solvent solution evolves towards the formation of an organic continuous network containing liquid. That's what we are going to get actually. That phase, that networking liquid, we can call it as a liquid phase, is called as a gel. That's what we can make it for the gel. That's what we can. In addition to that, here formation of metal oxide. Here whatever the gel is formed, it's a formation of metal oxide. Involves connecting the metal centers with oxygen or metal centers with hydroxy group. Here you look at now, oxy means here both the metals in between oxygen, hydroxy means OH group in between the metals. That's what we can call it as a metal oxides or metal hydroxo group. Therefore generating metal oxo or metal hydroxo polymers in the solution. Our main intention is to bridge between the metal oxide, metal oxo as well as metal hydro polymers in the solutions. After a drying process, then what we start after the formation of that metal oxide, we have to go for the drying process. The liquid phase is removed from the gel. When they are going to start drying, the liquid phase in that solution is going to start from the evaporating from the gel. Then the thermal treatment may be performed. After that, we have to go for calcination. That is another term, we can call it as a thermal treatment. Performed in order to favor to polycondensation enhance mechanical properties. When it is undergo for thermal treatment, it will undergo for polycondensation to give the mechanical properties to the material. That's what you are going to get actually. Yes, sol gel is an interesting in that it is a cheap, and why we are going to select this sol gel method means it's a cheap and as well as low temperature technique. That's what we are going to get actually. That allows for the fine control on the products. The chemical composition has even small quantities of the dopants. Yeah, that is a fine control of the products in the chemical composition. We can make it for the product with respect to proper composition. You know that chemical means we are going to make it for the whatever the materials we have, different materials having a different composition, but using the sol gel method we can make it for the product having a proper chemical composition. And in addition to that, we can add small quantities of dopants. That means organic dyes or rare earth elements can be introduced into the solution and end up in the final product finely dispersed. If you want final product, we can add small quantities of dopants. Dopants you are already used in that conductors, semiconductors, as well as the we are going to get finally the product is finally dispersed. That is the sol gel method. That's what we studied actually. It's a sol gel method. Now, if it is clear now that sol gel methods, that's one more method. We'll go for the inert gas condensation method. Shortly, we can call it as IGC, inert gas condensation. The inert gas evaporation condensation. Here, the inert gas evaporation condensation technique, in which in this method nanoparticles are formed via evaporation of metallic source in an inert gas. Look at now here, listen here now, the evaporation of metallic source in an inert gas has been widely used in the synthesis ultra-fine metal particles from 1930. See, look at now here now, the properties of inert gas condensation we are started using from since 1930s. In its basic form, what we can call it as this method consisting of evaporating a metallic source using the resistive heating. Resistive heating is the term. The inside a chamber which has been previously evacuated to about a 10 power 7 tar and backfilled with inert gas to low pressure. Resistive heating andre we are going for the slow heating. In addition to that, using that resisting heating, we can use for radio frequency heating or for the electron or laser beam heating, or whatever the all effective methods, whatever the all equally same methods we can use. Resistive heating you are going to use for the inside the chamber previously evacuated to the 10 power 7 tar and backfilled inert gas lower pressure. This is earlier, but in addition to that, we can use for radio frequency, electron laser beam, radio frequency, and as well as the equally effective methods. Now, the metal vapor migrates from the earth source. We are going to put the metal, that metal migrates from the earth source into the cooler inert gas by the combination of connective flow and diffusion, and evaporated atom collide with the atoms within the chamber, thus losing the kinetic energy. When the molecules or metal vapors are migrate from one side to another side into a cooler inert gas, combination of connective and diffusion of the evaporated atoms collide within that chamber. When moving from one side to another side, they will collide each other. Once they are going to collide each other, they are losing the kinetic energy. Ultimately, the particles are collected for subsequent consolidation, usually for deposition on cold surface. That whatever the molecules they are going to lose the kinetic energy, they are not able to migrate. Then they are going to deposit it on the collide surface. Now look at this figure. How we are going to make it for the experimental setup. This is main HU chamber, low pressure compaction unit. This is high pressure compaction unit, piston, sleeve. That's what you are going to get actually. Anvil, bellows, fixed piston, slide, vacuum pumps, funnel, evaporation sources. See, look at these particles. These are all metals migrating from one side to another side. Then what is going to happen? They are going to move from one side to another side. They will going to collide each other. They are going to lose the kinetic energy. They are going to settle down here. That's what we are going to, because here liquid nitrogen cooler. They are going to settle down here. That's nothing but what you are going to get actually. In addition to that, the most of the inert gas condensation techniques carry with this approach to extremes by cooling the substrate with liquid nitrogen to enhance the deposition efficiency. That's what we are going to get actually here the particular case. And the